setting up. So the next speaker is Ziao Wang from the Laboratoire Kastler-Bross, and he'll be talking about information theoretical local learning for physical neural networks.
Sorry, it's clear? Yeah, thank you. Yeah, first of all, I would like to thank Florian, Clara, and Anna for such good workshop and opportunity. I'm Ziao. I'm a PhD student with Wanjura in LKB at Paris. So today I would like to talking about our recent work on how to train cascaded physical neural networks locally, not the physical dynamic itself, but the physical network. So following the very well-known Nature Review paper recently, where we have a lot of authors here, there is kind of two types of physical networks. The first one is isomorphic PM, where the weight matrix of the neural network is one-to-one mapping realized by the physical platforms. For example, the memristor crossbar or MZI mesh. And for the second one, it's a broken isomorphism PM, where the physical unit provide a very useful, insightful, nonlinear transformation, but not necessarily to have some like differentiable digital twin. So there are some two cases for that. The first case is that you have some like trainable parameters out of the physical system. The physical system itself is fixed. And the second case is you have some like trainable parameters embedded in the physical system. So there's a lot of interesting and solid research around this field, and I'm not going to go through all of them, but each of them have a very good point. For example, like equipop or like Hamiltonian echo backpropagation, scattering BP, they don't need a differentiable digital twin. And such as for the PAT, they have a very good performance, and for each training step, they only need one physical pass through all the physical units. And for DFA or other zeroth order gradient, they have very loose assumption on the physical platforms itself. And also, like for the physical local learning and self-constructive forward learning, the good part is like the training is local, so you don't need the global gradient credit assignment. So for us, we would like to find the balance among these four factors. We want to do the local training. So if we want to do the local training, what kind of local feature we would like to have? So we want to go to have some insight from the information theory. The first one is information bottleneck. The information bottleneck is a common analyzed tools used in the neural networks to monitor the learning dynamics of the neural network. For example, it's basically measure the mutual information between the input X, the target Y, and the representation D generated by the layer. And during the learning dynamics, the neural networks first turn to have more complicated but more relevant representation to the task. And after a certain point, the relevance with respect to the task is still kept, but the representation will be simplified somehow. And this phenomenon is also the very similar phenomena is also observed in the language model, the LM. So for those who are not very familiar with mutual information, here is a very simple example. For example, you have a very lovely cat for your input and go through all the physical unit one by one, and finally your target is just to tell whether it's a cat. So what kind of good feature you want to have with mutual information? You want to have something like that is not a good one, though it has a lot of it has high mutual information with input. The target is not right. The mutual information IYZ is not. And suppose you have some beautiful building here, but it's not relevant with the input, neither the target. And this one is good because you can still tell that it's a cat. The IXZ is quite high, but the issue is the IXZ is quite high because it's still not simplified enough. And what you want is you want to only keep the essential information to finish the task. So this one directly translates into a local learning objective that you want to maximize the IYZ, the mutual information with respect to the task, and you want to minimize the complexity of the information. So here I would like to specify what kind of regime we are focused. So as we said, we have a lot of cascaded, not a lot. We have a cascaded physical networks, and for each physical unit, you can split into 3 cases. We only focused on the first 2, demonstrate on memory stir and optics. So to go through the physical information bottleneck, we call it PIP. That is like we have a cascaded networks. And for each feature generated by one physical computing unit, that is this one, we train it locally, and the loss objective only depends on the feature generated by this physical computing unit, and the input which we already have, and the target which for sure we already have for most cases. So then there is no dependence on the physical system itself a lot. And this is the loss function. So ideally, what we want to have is like during the learning dynamics, the feature we're moving from the input region to the target region in the Venn diagram. So the workflow of our demonstration is more like this one. We first local training the first unit, and after the PIP loss is quite low, we deploy the weight on the physical unit, and then we do the forward pass in the physical unit. We have, of course, we will have some like mismatch between the ideal one and the measured one, and we send the measured one to the second one, and we repeat the progress again, and then we finally have the last unit, and we have a linear readout layer which is trained locally by BP. So we use the matrix-based entropy to calculate the mutual information, which we only need to have single pass through all the physical unit. So the first demo is on the memory stir, which is an isomorphic unit. We have a 1024 to 128 memory stir chip, and we implement this one. Although we only show one physical unit, it is actually 3. So here we have we demonstrate on the MNIST and MNIST 1D. MNIST 1D is actually harder than MNIST. So of course, when we in silico training with BP and deploy on the system, of course you will have some accuracy drop. However, for us, the drop is quite small, and we still have a very good performance. And a more interesting test is like we have a cascaded physical unit, and we suppose there is one physical unit, the ADC, one of the ADC readout channel is broken. That is like one readout channel only generates random response. So ideally, the whole physical network will like broken. You cannot use it. So however, so you have some like accuracy drop for sure. And however, if you fine tune the other physical unit, the following physical unit with PIP, it will quickly recover the accuracy. And for the second demo, we demonstrate on the broken isomorphism unit, and here we use scattering optics, which provide the fixed physical transformation, which is unknown, and we don't want to have a differentiable digital twin for that, or have some like knowledge or assumption on that. And then we have a digital augmentation layer for the trainability. And this part is good because like the measurement is quite relatively cheap and fast. So we can actually monitor the learning dynamics. And the good part is like we somehow observe the very similar phenomena in the learning dynamics of neural networks. There, the representation generated by the physical part first fits with a task and then simplify the representation. And also we show that with more PIP steps, you can have a better performance, more PIP step on each physical unit. And because like the PIP is based on the distribution, so we also want to test how it behaves under the distributional error. So we test under noise, different level of noise, and also different size of data set. And also the out of distribution detection. So we can see, we compare with physical local learning, PAT, and DFA, which realized on the experiments. The noise is additive noise we add in the computer after we measure the response from the optics experimentally. So here what we have is like the PIP performs good in most cases, but like for the very high, very noisy setting is not very good. It's not the best. And for the small data set, it's also not the very good one because somehow it's based on the statistics of the data set. So somehow we need enough data set size. And for the OOD detection, it also performs good. And because, like we said, like we only depends on the task, so the task can be flexible. Previously, we only showed the supervised learning with classification, and we also experimentally demoed on the unsupervised learning and the reinforcement learning. So unsupervised learning is done by the memory register, and the reinforcement learning is done by the optics, which we can demo on some like very simple task. And one interesting point of the algorithm is that it does not need the response of the following physical unit. So you can actually localize each physical unit. And so we put them one in Paris and one in Beijing, and we put them together, cascade different physical units, and train them together. And because like we have some communication time, and the training does not need the response from the following, so we can actually do async training with PIP. So to better position PIP among all the algorithm, we would like to say here, like, it's not about the performance. I know the performance is the most important factor, but it's very hard to benchmark the different training algorithm on the platform, on different platforms, because like there are some like constraint of each algorithm. So for the left one, the axis like here, it means like the algorithm do not need any differentiable model for the physical part. And for this one, it means like the training is local. And for the right one, the X is like we don't have any assumption on the platform. And for the Y, it's like you don't need extra physical paths per training step. So although we are not the best for sure, but we still try to find the balance point among these four factors. So to summarize, we provide some like task aware local objective, and it demonstrates on different tasks across different platforms. And this work is a collaboration with Ziao Wang and under supervision of Huaqiang Wu, Sivan Zhigang, my advisor, and Chang Liu from Tsinghua University. So there's some outlook here, because like we do some like block-wise local learning, but somehow because it's local learning, it's greedy objective, so it's not global guaranteed. And on this point, we have some working, just like you can combine PEPIDA with that. And also we show that we can tolerate some imperfection from hardware. However, right now we only maximum demonstration here we did is only 1,000 by 1,000, and which is for sure is not enough for hardware. We need to do some million by million. And we also show like this is compatible with black box. However, the physical dynamics itself is fixed in our case. So if you want to train the physical tunables, I think you can also combine the PIP with equiprop ideally, and because you still need some guidance to actually train the physical dynamics. And thank you. This is our lovely group. It's co-supervised by Sivan Zhigang and Hilton Barbosa de Aguirre. Thank you.
Thank you very much, Ziao, for the great talk. Do we have questions? Faster.
The great talk. I've just got a quick clarification question on slide 15.
50?
15.
Yes.
Yes. Just to understand, could you please explain how you grade all these different models on these 4 very specific 10-point scales?
Okay. So we do the relative things. It's only like a qualitative, not the quantitative one. So the relative one is like we first set the base point is BP, the in silico BP, and you also set the ideal things is like you don't have any assumption or any model needed, and also just a purely local. For example, we do the relative thing. For example, like for example, the FFA and the self-contrastive FFA. The self-contrastive FFA and FFA, they do have the local things together. However, the self-contrastive FFA, they need the locality to happen, not in the last layer. And also, we also compare the DFA and the ADFA. And ADFA, they require some knowledge about to model the differentiable model of the forward physical part, and augmented it's for the augmented DFA. And DFA do not need a lot of this one, just like augmented DFA, they do not require the forward model to be weight matrix based. However, DFA strongly couple the learning dynamics to the weight matrix fashion. So, for example, you cannot train with, it's very hard to train with convolutional layer. And so it's relatively to compare different methods and put them in the position.
Thank you very much for the very interesting talk. We definitely have to discuss this also, because I always thought Hamiltonian echo backpropagation is the paradigm of completely black box,
yes.
But we can discuss this separately. Now I have a question about the mutual information. So in our experience, it's quite cumbersome to extract. It may still be fine if you have a discrete state space, but as soon as you go to continuous variables, and especially high-dimensional feature vectors, it becomes really difficult, actually, also in our own experience, just because of the difficulty of estimating entropies of high-dimensional vectors from sampling. So can you say a little bit about how you extract from your samples the mutual information efficiently?
Yeah, so basically it's not our work, it's a theoretical work from the computer science. So basically you can use a metric-based mutual information estimation. Previously, it's usually using some variational method to set the bound of the mutual information estimation or the entropy estimation. So this one is only data-driven. It only just observe the statics within a mini batch of the data set. It calculate the gram matrix of the feature in the mini batch and decompose the gram matrix and take all the eigenvalues. And with all the eigenvalues, you can calculate the rank E entropy, which you have alpha, and you take the limit alpha close to 1, then goes to the Shannon entropy, and then you can calculate it. So it's a matrix-based entropy. Yeah. So the bad part here is you need to do the SVD decomposition, but the good part is here the gram matrix is symmetry. So you can have some trick to bypass the to improve the very heavy computation. And however, it's not a nightmare, because here the gram matrix, the dimension is only based on the batch size. So when you have some data set of n and the batch size of b, the complexity here is O nb squared. So b is a constant number, and n is the size of your data set.